then please return 0. So that's what that 0 means there. So down here it says if you get B, and of course B is not inside this example, so it's going to return 0. So this idea of a dictionary is pretty useful, but the first thing, instead of talking about like the runtime performance or anything, he's going to talk about how you can go across the entire dictionary. And so what he's going to do is he's going to basically say that you can use a dictionary in the middle of a for statement. So here he's got a print histogram where he is expecting H to hold a histogram, our dictionary of these broken out letter frequency pairs. And then what he'll do is he'll say for C inside that histogram, print C and the histogram of C. Now what this is going to do is inside this for each loop, it's going to be pulling out pairs. It's going to be pulling out the keys, because you'll notice that right here at the H, he's not saying that he's working on H's values, he's just saying he's working on H, and the default will be to pull the keys out of this, this histogram here. So he's going to get each key, and then he'll print the key and the value in the histogram for that key. And so here he is assigned the histogram for parrot to H, and then he prints it. And it comes out with 1 A, 1 P, 2 R's, 1 T, and 1 O. But what is interesting is that this order of the frequency is not going to be guaranteed, because we only talked about how it maps from one domain to another. There's no natural way to go across the elements as the keys. So what he'll do now is he will take this histogram, and of course he's not referring to anything in particular, so it's talking about the keys, and he will sort it and change the for loop to where it is now doing a sorted set of keys and going across it and then pulling them out. And that will give it in alphabetical order. All right? So if you have an object in there that naturally sorts across something, like generally characters are sorted across alphabets, then you will get things out in a natural order.
So can you sort both keys and values?
You can, but not at the same time. Because if you sort by one, there's no guarantee that the other one will remain sorted.
But how do you distinguish? How does the dictionary know which one you want to sort by?
You have to specify it. So, like when he says sorted H right there. All right, here, let me do this. So he said it was sorted, right? Yeah. So let me do that histogram once upon a time again, and this time we'll store it into hist1. Okay? If I were to say hist1, because, whoops, it's going to print out the representation of the histogram, okay? If I were to do the keys on it,
okay,
then it just prints out the keys. Likewise, if I did the values, it would just print out the values. Now, because sorted will need something. If I were to do, say, for key in hist1, print key. I forgot the parentheses. Okay. For key in hist1, print key, you can see that it's just going across and printing out each one of these keys. All right? But if I were to say for key in the sorted hist1, print key, then it will sort these. Now, the space character happens to have a lower value than even the letter A. So that first line being blank is not a mistake. That is the space key being printed out. If I wanted to make that clear, I could probably do something like I think that's the right, oh, no. Got the concatenation operator as plus in this language. Now you can clearly see that the space is the first key. All right. So did that clarify that bit for you?
Sure.
Fantastic. So reverse lookup. We just said that dictionaries cannot be reversed in general. So what he's going to do is he can't reverse the dictionary in general. Instead, he's going to walk each key looking for a value that matches the one you asked for. And that value is going to then cause this if statement here to evaluate to true, and it will return back the key in the middle of its walk. Now this has a perhaps subtle or perhaps not subtle issue with it, which is if you had two keys with the same value, no one knows which key it'll run into and return first.
But you said you couldn't have two keys of the same value.
You can have two keys with the same value, you cannot have one key with two values.
Oh, sorry. Yes.
Yeah.
Sorry, I got it back.
No problem. And then, of course, if you get to the end of this loop, then he will raise a lookup error. Okay, he'll construct a new object and basically throw it. So here, he's using his histogram for parent, and you can see that he uses this reverse lookup here. All right? And he's captured the key with some frequency of 2, and it's R. And then he tries a key for a frequency of 3. No letter is in here 3 times. And so it's going to come back with a lookup error. No key was found with that frequency. Can we? Is there anybody that's got any difficulty following that example? Nope. These are some pretty well laid out progression, except that I don't really understand why reverse lookup was chosen as the way to go. I think the main thing that he wants to cover here is that you can basically iterate across the keys in the dictionary using for something in the dictionary. Now, dictionaries don't have to store strings or characters or numbers. They can store just about anything. So any object inside Python can be the value of a dictionary, including a list.
Sorry, the value of a dictionary is a defined type of structure. When you say it can be anything, you mean the value? The dictionary is always a key value.
Yes, it is.
Right.
And there's constraints on what the keys can be.
Right, yeah.
Okay? But there's not constraints on what the values can be.
All right.
So the value can be any Python type.
Yeah, okay.
However, the keys themselves, it's going to be a different story. All right? So basically here what he's doing is he's creating a list. You can see that instead of, like this is almost the histogram example, except that instead what he's doing is he's pulling out the value here, okay? And he's definitely setting a set of keys. So this is not not exactly the same thing as the reverse of the dictionary, but what he's doing is for every value, he's now appending the keys. So before we said that the dictionary, maps one way, and we said something like 5 maps to 25 using our x squared mapping, and -5 maps to 25, which is the same thing because these are sets. There's only one of each individual unique thing in it. What he's saying is, oh yeah, since we can't really reverse it, what we can do is we can come up with something that is the set, the list of all keys with that value. So he reversed it not exactly the same, because that would mean that this 25 would have to go to both 5 and -5, and that's not a map anymore. Instead, what he did is he basically said, we'll build something that's functionally useful. And it'll just basically, it's not exactly a reversal because obviously this is a list that the key is pointing to, and over here, nothing is a list. But you can capture all the keys in this way. And he's demonstrating two things at once. The most important thing to come out of this, though, is not really that this is a useful technique, because if you have to do this a lot, you're probably picking the wrong data structure for your problem. But that the dictionary itself, the value can be an array. It can be another dictionary. It can be a list. It can be an object. It can be a string. It can be a character. It doesn't really matter what it is. And so here he's trying to show that starting off with this dictionary, using his algorithm, all right, he now has a flipped version of it where the key is 1, and 1 has 4 elements in it that include A, P, T, and O. Okay? And 2 has 1 element in it that includes R. And these 0 through 3 and 0 here are supposed to be the indexes. And we talked about indexes last time into the lists. And of course, if you dump them out, you can see that the key 1 is associated with a list. And the list has all of the letters that previously had a value of 1. Now he's going to talk about the next part, which is basically, we mentioned that while the value can be anything inside a dictionary, the keys cannot. All right? The keys in a dictionary are actually used by the routine that's behind the dictionary in order to store it for very fast access. And this means that the keys are hashed. How many of you understand what hashing is? Okay, then it's worth a few minutes to talk about it outside of the context of this book.
Secure?
You know, hashing can help make something secure, but it usually doesn't. It's just a technique about a different representation. So if, yes?
I would argue there are, some kinds of, there are 2 kinds of hashing. This is one just to, I guess, designate the key. But there is hashing. You can have like a huge contract, say, and then you have a hash value that's associated with it. You send that contract, and separately that hash value is known. So somebody can compare the hash of that contract with that hash value and determine that, oh, there have been no changes made to that contract. So
That's
there are 2 ways.
almost a true statement. Okay? And the
It's done
reason that it's
correctly, I think
almost a true statement is what I'm about to talk about now. Because we need to get an idea of what a hash is. So, what if we took this whole thing that we kind of talked about domains and mapping and stuff like that, and we said that we had some sort of big bag of all possible values. And this bag pointed to something generally a lot smaller of numbers. Okay? But the way that it did it, if there was any one value here, it was guaranteed to point to a specific number. Not some random number, but a number that was comprised of the value. Now, there's no guarantee that another one doesn't point to the same number. So that's the only reason why your contract example would fall apart.
Well,
But-
of course, they do it so if it's done correctly, it's exceedingly rare.
Right, so like Java uses integers for their hash values. And so it's something like a 1 in 4 billion chance. Okay? And Python, I'm not sure what the number is behind it. And it is extremely rare, but it's even more rare if you use numbers that are bigger. Because eventually, a hash has a limited range of values. They're not going to use any number, because then it would be equal. It would be like an infinite number of values on one side and an infinite number of values on the other. And you could just have a perfect identity mapping, 1 to 1. All right? So instead, what they're doing is they're collapsing it down to a number, and there's a very important reason why they want this number. And this has to do with how you actually build things under the covers of a language like Python. So when you have a list, to search the list, you check the first thing, and then you check the second thing, and the third thing, and the fourth thing, and the fifth thing, because there's no guarantee that you'll find the thing that you want in the first slot. And if you tried to go to like the middle of it, you may have skipped over it, because lists are not guaranteed to be in any particular order.
Sorry, could you go back to what, like right now you're talking about, you're evaluating a list?
Yes, so
Right.
we're trying to find a value inside a list.
Okay.
So the only way in which you can find a value inside a list without any extra knowledge is to check every element in the list. Okay?
Iterate through the list.
If you check every element except one, it could be that last element that you forgot to check. So you just generally have to go through every element in the list. Now, if the list is sorted, you can skip over swaths of things because you know that, like, checking the middle, you can throw away the top half or the bottom half. But for a generalized list, there's no guarantee that it'll be sorted. And you have to check every one. And this gets really slow when you start getting lists with a lot of information in it. Okay? Pulling this element out of the list, checking it against a value, pulling the next element out of a list. It's not too bad when you're pulling out like 1,000. But when you're pulling out like 1,000,000, you can start to watch the seconds tick by as you're searching for it. When you're pulling out 1,000,000,000, you can watch the hours tick by as you're pulling stuff out of it. So the whole point is that there needs to be a faster way to hold information that's much, much, much larger. Okay? And so what happened is someone came up with this very clever idea of a hash table. In a hash table, instead of having this list of things that you check one at a time, they said, well, if we could make the list smaller, then basically walking the list wouldn't be so bad. But we would have to know which list to start looking at first. And so what they did is they took this value here and mapped it to a number. And then they created the hash table. Okay, let's say this hash table is 8 buckets long. So they'll do modulus division against 8 and get a remainder of 0. That means that the 0 element is the list that you will be checking. I have now just sidestepped 87.5% of all values. Because this V maps to some number.
You threw in all sorts of stuff there at once. I'm still,
It's a complex idea. It is not easy to pick up at once. So we'll just go through it again. If I can make a number, all right, out of a value,
that's or the quote value. Each one of those things you're taking, the hash table, is each thing a number, or could it be, like right now you have, let's say you have 1 million things. Are you saying each one of those million things is a number, or could it be any kind of thing?
Each one of those million things can be passed to a routine that comes back with a number.
Let me make this a little bit simpler. How many people in here have heard of MD5? Hands up. Okay, so MD5 is actually a hash, right?
Yeah.
Right.
You can give it a lot of crap. You can give it whole files, torrents, whatever, ISOs, and you get that MD5 number out the end of it, right? That number represents that file, and when even one bit in that file changes, you get a whole new number.
Yeah.
And the whole purpose of that security behind MD5 or SHA-1 or these types of things you see, is that if anything in that file changes, you get a whole different number. That number is a hash number. If you put that number in a table, you can take that file and find where its entry is very easy. And if you have that number, you can easily look in the table and find out where that file is. Right? Because you now can represent this gigantic file or this CD-ROM or this picture with just simply a 40-character number. So what Ed's talking about here is that internally with Python, when you give it a key, that key undergoes a similar process, except it's smaller than a SHA-1 or an MD5, and it's faster. It's not as secure, but it undergoes that same type of thing. And then Python writes that number internally. And when you later go to look it up, Python just has to say, what's the number for this key? It gets that number again from that key, and it can go right into that table looking for just that number. It doesn't have to go looking for the whole ISO or the whole JPEG or the whole MP3. It just has to get that number again.
Yeah, it just jumps to the subsection of the list in this kind of a data structure that might contain the value. Now, the thing is that because the implementation in Python, the number that you get is much smaller than some 40-character huge number, the chances that you reuse the hash is higher. So what it does is it will go and it will look and compare each one of the values in here to see whether it's equal to the key that you asked for. And when it finds the matching key, then it knows that it found the value. Okay, and this will take something like that 1 billion things that we talked about in a relatively small hash table of, say, I don't know, a couple hundred entries. You'll get maybe on average a lookup of around 20 or 30 things, but well, a little bit more than that, about 100 things. So you don't check 1 billion things to see if you can find something. You just check 100. It's incredibly faster. And this is the reason why hashes are fast. And hash tables or dictionaries are fast. So the entire concept that I was complaining about before, about walking over each key in a hash table, this sidesteps the point of using a hash table. Use a hash table when you need to store something and you need to get something out real fast. But if you need to keep each key and walk through each key, you're not using a hash table in the way that it was built to be used. But he wanted to show that he was reversing it.
Oh,
Yes.
I guess in the case you just talked about, use a dictionary when the value of the key has some kind of inherent meaning about it, like it's a name or something. But a hash table, it just gives you a number just to make lookup easier. But the key itself, in that case, doesn't have any inherent meaning other than it's unique and it's a number.
So Python basically calls hash tables dictionaries. They're the same, effectively. I mean, some of the older hash tables could only use lookup by the hash value, but most of them can be looked up by anything that you can turn into a hash. It's just the mechanism underneath the cover will get you to the value much, much faster. And so as you start working algorithms, you start working on solutions to problems you have. You'll probably start off with a couple of lists. And then you'll start to recognize that your lists aren't giving you the performance you need, and you might try to restructure it in such a way that you can directly look up things that you need, as opposed to walking through entire collections looking for specific things. Okay, so let's go back down to here. So here, he's saying that dictionaries are implemented using hash tables, and that means that the keys have to be hashable. Now, he doesn't actually define what hashable is in ways that Python implements it. He just indicates that you write some sort of a function that would return an integer. Okay? And that integer, okay, would be called the hash and be used to look up the key value pairs. The way it's done is with division. You divide it against some sort of number, the number of buckets you have, and whatever your remainder is the bucket that you start at for that value. And the way that Python implements this internally is all of the objects have support for a call, a method called hash. I guess I wrote over myself. So. But there are some objects that don't return back proper numbers. There are some objects that either, I think they throw exceptions. I could be wrong. We could double check real quick. So if I want to say hash, this took this ABCDE string and came up with the number. Now, if I were to call that again, this is not a random number. It is a number that is a representation of this value. So I can call this all day long, and I will get the same number. But if I were to change one of those letters, I get a different number. I change the E to F, and now I get some sort of negative huge number. And if I go back to changing it to E, I get the same number I had before. Okay? One of the problems with lists is that lists are mutable. Remember, you can change the elements in a list? So when you try to hash a list, it's going to fall apart, because you could say something like x equals A, B, C, okay? And then you could say something like x sub 0 equals D, and then you can print x. And you get DBC. This means the value is changing. So this number isn't stable for a list. It couldn't be stable. All right? And this means that basically anything that is mutable, anything where you can change the values but not actually have a completely different object, is not going to be usable as a hash key.
Why isn't it a different object? Like in the example you just gave, why it isn't? It seems like that is a different object.
It is a different value, but it's still the same object I initialized here at x.
But it has it's x, but with different values.
It's x, but with different values. And the difference between an immutable thing and an immutable thing and a immutable thing is that it's impossible to have the same thing with different values if you're immutable. You have to have a different thing. For example, the number 5 is immutable.
But if x, you could say x equals 5, and then you could hash x, right? And then you can reassign the value to x and hash it and get a different value.
Right.
So,
But what I'm doing, if you'll remember, is I'm not actually hashing the variable. I'm dereferencing the variable. I'm getting the value for this variable, and then I am calling the hash.
okay.
So this is the same as saying 7 hash. Okay, which is not valid for Python, but the point is this is the concept of calling 7 hash. All right? It's not valid because the numbers are not correct identifiers. And you can't call the dot off of a
You can
correct
hash a list,
identifier.
but you can't hash a number?
No, you cannot hash a list.
I thought you,
Think of a list as a backpack.
I'm sorry.
If it's based off of the values of the things inside the backpack, and you're changing the values of those things by putting stuff in and out of your backpack, you would have to get a different number every time you hashed it. Well, if you're storing it in a table at some sort of an index, if you change that number, it's not going to know to relocate those values in a different place. So hashes only operate inside a dictionary on immutable values. Okay? Now, there's ways in which you can store things that look like lists, but they're not lists. And we'll get to that in the next chapter. So the point is that it works fine if the keys are immutable. We talked a lot about that. Does anybody have a misunderstanding or need more clarification on what immutability is? No? Yes? Okay. So, but if the keys are mutable, as they are in lists, you can't do this, because if you were to try to create a key value pair, Python is using the hash of the key to store it in this underlying data structure. And that hash can't change. Otherwise, when you try to pull it out, it'd be in a different spot. And so this is the reason why all dictionaries are going to require immutable keys. And not just in Python, in other languages too. So here is a Fibonacci example. In the old example that he talked, the old programming thing that he did a long time ago, he talked about how to solve Fibonacci recursively. And it took a lot of time to solve some really big Fibonacci numbers, because you basically do things like, in this, calculate the Fibonacci of 1 3 times, 2 a couple of times, 3, and so on and so forth. So what he's going to do is he's going to basically say, hey, there's ways of speeding that up. And what he's going to do is called memoization. And memoization is a complex idea, but it's not very complex to understand or talk about. So basically, if you have a function that you are likely to use over and over again, you can store the input to the function and the value of the function in a dictionary. And instead of actually calling that function, you first look up the dictionary value and then sidestep calling the entire function. And just swap out the value. In that case, now when he calculates Fibonacci of 0, he's going to store that into his dictionary of memos. And when he calculates Fibonacci of 1, he will store that in his dictionary of memos. And when he calculates Fibonacci of 2, it's going to say, oh no, I already have values for Fibonacci of 0 and 1 inside the dictionary. I'm not actually going to recursively call the function and perform the calculation again. I'm just going to swap out the value. And doing this, by the time that you get up to here, these calls are free. And so he's speeding up using a technique called memoization. And so he's saying, hey, now we'll redefine Fibonacci for a number. If the number is in the known dictionary, then just return the value for the known dictionary. All right? Otherwise, we start calculating the Fibonacci of that number minus 1 plus the Fibonacci of that number minus 2. Now this is a recursive call, so it'll come back in here until it hits known. All right? So what did he have to do? He had to initialize known with a couple of values to guarantee that it lived.
Yes.
And so this is, you know, we talked about recursion. Yes?
Why doesn't he use the else keyword if he's using the if in there?
Because he's using the return keyword, and so his execution flow will leave this function call at the return. So he could have used an else keyword and then indented everything, but there is no way that after hitting this line of return, he can get to the lines below.
Oh, okay.
So he saved himself the typing of the else and then just shifted everything forward. Okay. And so here, once it does calculate this Fibonacci, he stores the result into the known, so it's been memoized for further calls. A long time ago, they used to call this dynamic programming, but now they just call it memoization. And if you didn't initialize this known, it would go on for forever. Matter of fact, if you called it with a negative number, it would go on. So here he's saying that now he's used this technique called memoization, and it says whenever Fibonacci is called, it checks known. If it's already there, it returns immediately. Otherwise, it computes a new value, adding it to the dictionary and returning it. Now we have, we've kind of talked about how he's introduces a lot of things kind of all together, and it sometimes comes out jumbled. Most people actually know how to use dictionaries before they're even introduced to memoization. It's a technique that you can use to speed up certain kinds of programming problems. But it's not something that you would probably use in lots and lots of scenarios, unless you could guarantee that the input always returns back the same output, and you're going to be calling the same input over and over and over again. All right? Most people don't use recursive solution for a lot of things, and therefore they're not going to possibly be calling the same input over and over again. And then, of course, because global variables need to be discussed somewhere, and there's no better place than to discuss it in a completely unrelated topic like dictionaries, he introduces global variables. And global variables basically, remember Python, the scoping? Who can tell me the scopes in Python?
Function scopes.
Function scope?
Global scope.
Global scope, right? So here he's got a variable up here, verbose equals true. Which scope would that be?
Oh,
Global, good. All right? And down here, he's referencing that global variable. All right?
Where do you look? Wait, you were. Show me the verbose thing. Oh,
Right here,
yeah. I didn't see it
verbose
above
equals
it.
true.
Okay, yeah. The equals true thing. Gotcha.
Okay, and then here he's referencing verbose. And because it's not been used inside this function, it's very obviously only going to be found in the global scope, or not found at all. But over here, he uses bin called, and he wants to assign it. But the problem is that by putting this name here, he's created a second variable called bin called that is inside the function scope. So this function scope bin called gets set to true, the function exits, and the global bin called remains false. Okay? There's a way of fixing this. You can basically declare that your bin called within this function is going to resolve to the global scope. The only reason he's doing this is because eventually he wants to get down to examples where he keeps dictionaries in the global scope. Generally speaking, the more global scope you have, the harder it becomes to reason about your program. Reasoning about your program is the most expensive part of writing a program. Reading what you wrote, okay?
So you said reasoning about your program is the most expensive part of writing a program?
Yes. I can type at 65 words a minute, okay? The number of times my fingers hit the keyboard is not the most expensive part of writing the program, okay? The figuring out whether or not my program is performing a particular function correctly, or processing data correctly, or trying to read my program later, all of these take more time than me typing on the keyboard. This is the reason why you want to make your programs very easy to reason about. And if you have a variable that is inside a function scope, then that means that you only need to read the function to figure out what the variable is doing. But if you have a variable that is inside a global scope, you need to read the functions that use it and all the other functions that might use it. Which means you're on an Easter egg hunt for all the functions.
Yeah.
And you start saying this function doesn't use it, this function doesn't. Oh, here's another function that uses it. How do these two functions interact with each other? Does one get called first? Does the other get called? Do they have to be called in a particular order? And next thing you know, you realize that global variables greatly increase your mental carrying capacity for what the program is doing. It makes it very hard to reason about it. Yes?
And with global variables, after you've eliminated everything in that file, you go search all the other files for the project.
That's right, because global variables are global everywhere. And it gets worse.
Huh.
Because you may not be the sole author of your program. So eventually you decide, hey, I'm going to work on a programming team. And that programming team, someone else may have decided to use a global variable.
Whoa.
And it gets better. You'll be like, well, we'll try to modularize it. Well, guess what? You'll be like, it's time to finally rip this global variable out. Except some other team decided to use the stuff that you wrote and is now interacting with the global variable. So you finally cleaned it up and made it not global, and this other team starts complaining, hey, you broke our stuff. So please, think twice before you use a global. It's not that hard to use a past parameter.
Well,
Yes?
given that, can you talk about what are the criteria for properly using a global variable then?
You want to be killed by your fellow programmer.
So that really, almost any program, you don't have to use you really don't have to use global variables in programming, or there's
All programs can be restructured in such a way that there are no global variables. Okay? Now, you may be dealing with a library that already made design choices that force you to interact with global variables. For example, in C, they decided that it was really inconvenient to figure out how to do error handling. So they stuffed a number into a variable called error node, because apparently even NUM was too much description, so it's just ERRNO.
Gotta conserve those bytes, man.
I mean, you know, and in character counts, especially when the compiler is going to rip that freaking name out of there anyway, and it won't be in there. But the point is that this error number is a global variable. So when you call something and then there's a chance that it raised an error, you're supposed to check this error number afterwards to see if it's 0. And this is just how C is structured. And it's because they already were using the return value for some things. Like if you call the square root of a number, you're going to get that return value back. Okay? But the point is that this makes writing code in C that actually checks for errors far more painful than it really should be. And other languages that don't use this technique, you know, they suffer in other ways, but they don't suffer in that way. Okay, so here we are. Again, here is somebody trying to update a global counter. What can you tell me about this that's wrong? What is the part that makes this not work?
That you can't see it outside of the function.
Exactly. The fact that they use this count here as an assignment means that they declared count and initialized it to count +1. And so that means that this count here is scoped within the sub. And this count here, which count does this scope to?
Function scope.
Which one?
Function scope.
Right, because it's just been declared, so it's going to bind to the function scope one. Now, if he had not named this count, if he had named it something else, then this count would have gone to the global scope because it couldn't find it inside the function scope.
Would count plus work as intended?
Now, count plus, that would work because you can only increment a value. You haven't declared anything. You haven't initialized anything.
So how would that work then if it hasn't been initialized?
Well, but it has.
But it has. It's been initialized outside of the
scope
of the sub of the function, I should say.
Just hold your breath and keep reading, because that's where we're going to hit this.
Right. So here he declares global count, and he uses an increment operator to increment it by 1. Okay? And so that just, you know, that's the fix. Again, known is up here. Here he is referencing the second element of known and setting the value to 1. Okay? Or I should say, known is a dictionary, so he is setting the key to the value of 1. All right? When he does this, he's saying that you can add or remove or whatever, modify the known, but if you want to actually replace it, you have to declare, you have to specify which known you're doing. Because here, do you see this assignment? This is assignment again. It would have been a local known if he had not declared the global. Does this make sense? And then he talks about debugging. And these are generally good ideas. You don't want to have too much input when you're debugging, because if you're trying to debug a small 5 or 6 sort of example thing, works out really well. But if you're talking about like, you know, oh, Evan, I think we got somebody at the door. Okay. But if we're talking about, you know, debugging against your actual data set that like maybe has, you know, 500 records on it, you're probably not going to be able to find that one right record. very easily, and you'll have too much output or too many things to walk through. So you like to scale down your input. Check your types. It's a loosely typed language. Actually, it's a dynamically typed language. It's strongly typed, but it's dynamically typed. So use that type operator in order to make sure you're dealing with what you think you're dealing with. And every now and then write some code to check for errors. And then, formatting your output, you can use the pprint in order to recursively dump data structures and make sure that you actually can see that this is a dictionary, that the values are arrays that contain dictionaries, that the values are whatever. So we covered mapping, the concept. We covered dictionaries, key value pair, items, which is something in the dictionary.
It looks like maybe the Evan and the delivery passed each other.
Oh, no
different
problem.
elevators or something.
No problem. That's fine. All right. And we're just basically at a really good place to wrap up dictionary. So we can talk about the examples if you want, but I think we'll take a break and get everybody some food and then pick up from there. Who knows what a tuple is?
Tuple.
Awesome. Tuple is usually a... Okay, well, I was expecting a pair. Python, actually, tuples are more than pairs. Tuples can have multiple values or one value. And you're right, they are immutable lists. So before, if we wanted to assign a comma-separated list of values, we usually threw the square brackets around it and turned it into a list. However, you can use plain old parentheses, and if you do plain old parentheses, then you're basically going to get a tuple. If you don't put anything at all, it'll assume that you assigned a tuple. Okay? So here, let me show you real quick. Okay? Now what's the difference between a tuple? Well, okay, you already answered it. You know that it's immutable. So the point is that you have this tuple thing. Now why would we have lists and tuples? Because the only difference between the two is the immutability. Remember that we can't use compound keys inside our dictionaries if they don't resolve to an actual hash code value. Tuples, since they don't change, we can basically take the hash code of each thing in the tuple, run it through another little math algorithm, and come up with a stable hash code for the whole tuple. You can't add an item to it, you can't remove an item to it, and you can't change an item in it. So this means that tuples can be used as keys for hashes. So here they're showing that you can basically use that whole string as a sequence of characters thing and create a tuple out of it for characters. And because tuple is a built-in function, don't use it as a variable name, please. Okay? It will cause no end of fun and confusion. So a lot of the list operators work on tuples. This is to be expected because we conceptually described it as a immutable list. So indexing works. This will pull the first element index 0 off of it. Okay? Our slicing operators work. Remember slicing? So we're talking about element 1 up to 3, not including, because slices don't include the terminating index. But if you try to modify a tuple, you're going to get an error. And that's because this assignment operator actually isn't implemented for the tuple. It's going to always die. All right? Now, what you can do is you can construct a second tuple off of the first tuple, replacing elements. But that's not the same thing as what you would do with a list. With a list, you just set the element inside the list, or add an element to the list. This is not possible with tuples. And so here what they are showing is that they are constructing a second tuple off of the first one. They're using the hash slice. So they're going to pick from index 1 onward, which is the second and everything else. And then they are going to replace the first one with the element A. Okay, and so now they have managed to uppercase our A, B, C, D, E, but this T is not the same tuple as it was before. It is a completely different tuple. It may be stored in the same variable, but conceptually, it's a completely different thing. So tuples are ordered. Okay, they're ordered off of the indexes and the index values natural ordering. Now, does this mean that you can construct a tuple of arrays? No, you can't. It's got to be immutable all the way down. All right? So here, it's going to compare 0 to 0 first, and then 1 to 3, and of course 1 is less than 3. And so it will say that, yes, 0, 3, 4 is greater than 0, 1, 2. There's no need to compare afterwards, because it found the first thing that would trigger the comparison operator. Okay? And here, it's still less than, because 3 is still greater than 1.
There's a question over there.
Sure.
Oh, what's a classic example of a tuple in action where you might typically use tuples?
So let's say you wanted to store a person's name, but you, like first name, last name, but you wanted for convenience not to have to pull those names out of a string through parsing over and over again. So you might split the string on a space, capture the first name and last name, and store them as a tuple. And generally that would work okay until somebody gets married. But, but the point is that generally, like, say like you're describing a point in XYZ coordinates. If this point is not something that can be relocated, okay, then it might be worthwhile doing it as a tuple. You know, just any kind of scenario where you have a list of items that you might want to capture. And those items don't have to be just numbers or just strings. They can also be other things that are immutable. And so, just generally speaking, you could use a tuple for capturing any kind of structured field.
You typically store it, or is it's used on the fly, like?
It depends on what problem you're solving.
It's irrelevant. That's irrelevant, right?
Right. I mean, like the approach that you're using, if you're like creating some sort of a database and you're trying to query it, then you might have the input actually typed in, construct a tuple off of that, and then look up that key inside a dictionary. Now, that's a very contrived answer, but you know, there's only so much I can do on the fly. It really depends on what you're trying to solve. So there's nothing very special about tuples in assignment, except that tuple assignment takes one tuple and allows you to remap it to another tuple. So in this case, the value of B will get assigned to the value of A while the value of A gets assigned to the value of B. This is a concise way of writing swap the values of A and B. Because what you're doing is you're taking a tuple on one side, something and something else, and you're assigning it to a tuple on the other side. Remember, the parentheses are optional in tuples, like we showed on the example. The parentheses are optional. So if I wanted to do something like 1, 2, 3, equals Ed.
Do you want quotes?
I've declared a variable called 1, 2, and 3, different variables. And remember Ed, I stored A, B, and C into it. So Ed is a tuple of 3 elements, and I am now doing like a mass assignment. A will go to 1, B will go to 2, and C will go to 3. And so it's a really convenient way, if you've got a list of items, to assign them to individual variables in one line.
Do you made a dictionary?
It's not a dictionary because it's 1, 2, and 3 are not part of one kind of type. Okay? It would be a dictionary if I said something like okay, you see how the syntax is so very different.
Yeah.
Okay, and this means that there is no variable called 1 in this example. There's a key called 1. All right, but the tuple assignment, I actually created a variable called 1. And so 1 is a variable. I could do the type of 1, and it'll say that it's a string. But if I do the type of dict3, it'll say it's a dictionary. Did you follow that?
Yeah.
Okay, good. So, when you're doing tuple assignment, there's the problem of arity. You might have more things on one side than on the other. Okay? Some languages just drop the extra elements, but Python won't. So if you're used to that, don't expect that. Instead, you will get an error that says you've got too many values to unpack. You've got this tuple of 3 things here, and you're unpacking it into 2 different variables, and you can't stuff 3 numbers into 2 variables. So you get an error. And of course, the right side of a tuple can be pretty much anything. It can be a sequence of strings. It can be, any kind of a sequence. So here, they're using the split operator. Remember we used that when we were talking about strings? To cut out this @ sign. And it'll return back 2 items. It'll return back an array of length 2. And then we're going to basically, that array will be treated as a tuple in order to do multiple assignments. So the username of Monty will be split off the email address, and the domain name of python.org will be split off of the email address. And that has to do with multiple assignment right there. Tuples are not the only things that can do multiple assignment, but they're generally the thing that you wind up using the most. Now, sometimes you want to return more than one value. In some languages, this is not permitted. Like if you're working in C, you can only return one value. So you'll return back a reference to a data structure that contains multiple values. But Python actually supports effectively returning multiple values, because really what you do is you wind up returning a tuple of all the values you wanted to return. And so here he's created a function called divmod. I'm sorry, it's a built-in called divmod. And what it does is it's going to divide the number and provide you with the remainder. So the mod operation typically gives you the remainder of a division, and the div operation usually gives you the integer division. Not the fractional division, but the integer division of a number. So here, 3 can go into 7 2 times with a remainder of 1. And so the result is 2 with a remainder of 1. And if you wanted to leverage the multiple assignment pattern, then you could actually, instead of capturing it into a variable that shows itself as a tuple, you could unpack the tuple into a quotient and a remainder. Now, min-max, it is sometimes useful in some kinds of math computations, but for the most part, sometimes it's not. Like if you wanted to get the range, so like you could have a whole bunch of numbers in T passed in as a tuple, and this will give you basically the range. It'll give you the smallest T and the largest T. And so here, calling it, you can see that 0 and 7 will eventually get filtered out, and you'll get basically the outer limits of this list of numbers, or this tuple of numbers. Now occasionally, you don't know how many items there are going to be. Okay?
How many items in the tuple?
Yes, how many items in the tuple, because you notice how I called that. I called it very carefully. The first set of parentheses is for the function. And then the second set of parentheses inside makes it very clear this is one tuple. And so this entire tuple will get assigned to T. All right? But occasionally, you might want to pass in a variable number of arguments. For example, when I pass this T in here, there's no indication on exactly how many items are in there. And so what happens is in some language, there's things called variable arguments. Now, Python has them, but they don't call them var args like you do in C or other things like that. Instead, what Python does is it uses an asterisk to indicate that the remainder of the arguments that have not been captured into other things go into this last element. So right here, we don't have a variable before args. This means that all of the arguments go into args. And args will be a capture of the entire tuple of all of the past parameters. Who didn't follow that? Awesome. So,
but when you use the asterisk this way, it only refers to tuples, nothing else. This kind of asterisk.
So this asterisk is shorthand for we're going to store more than one thing into this variable, possibly. So I can call this function print all. I can call it like that. Notice there's nothing in the parentheses. I can call it like this. And I can call it like this. Now normally, I would have to have 3 variables in my definition to capture these 3 values. But because I use this asterisk, I am going to gather the remaining values into args. Okay? And it will construct a tuple because you can't change the numbers that you pass to the function they'll eventually be collapsed down to values because it's a call by value system. And those numbers can't change. You know, you started the function with those numbers, those numbers are assigned to args. So this args will capture as many items as I pass to it, and then pass all of those items into print. Okay? And obviously print would have to be defined somewhere with an asterisk in front of it too, or else things are going to fall apart. So when I was saying that, notice that when I called it, I put an extra set of parentheses around it. That made all of this one thing pass through, which is the reason why I wasn't using that asterisk or the star in front of my variable name. Now, this kind of parameter passing, it doesn't mean that you can't have other parameters. So you could do something like this inside the parameters of some function.
So you'd always have to, in that case, you have to pass one or more.
Or if you didn't pass any, then all of these would basically be unassigned. But you would have to definitely pass like nil, comma, something, or just one or more. You're absolutely right. One or more.
Maybe it would be good, because that example where the extra parentheses are needed, maybe it would be good to show a few more examples that are needed, like when you're doing a format string into a function.
You want to take out an F and put a colon there too for, I don't know, in case you're being filmed.
Like that?
Ask the man of camera, I think so.
Well, you were the one with the question, so I'm asking you if that's what you were looking for.
That'll do.
Okay, so like right here, if I call this min-max, let's do something. Let's say I've got a sequence, all right, and I'm going to declare it to be 1, 5, 7, blah 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 blah. Da, 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 da.
Did you see that?
Okay.
Yeah.
Oh, wow.
There we go. So now I've got a sequence and it's a tuple. And if I print my sequence, you can see it's a tuple. It's got these curved parentheses around it. I can't change it. I can definitely print something like an index off of it. Okay, so we'll print like the fourth element. Remember, index is one less. Okay, and so we're printing this 6. And just to prove that, since I happened to pick an element that was duplicated, let's do the 5th element. And it's 8. Okay? And so this is in one variable. So if I were to pass like min-max sequence, it's not very hard for min-max because you see that up here where I defined it, it took one parameter. But if I wanted to do min-max like this, this won't work. Because here, it's very clear that I have more than one parameter. And so it doesn't know how to match these values up to the parameter in min-max. Now, if I were to change that to where I pass in one parameter that just happens to be a tuple, it'll completely work. But this kind of extra parenthesis syntax is painful to write for a lot of people. You need to know like which functions require one set of parentheses, which functions require 2, and it's just generally not very easy to rationalize because you're basically memorizing a lot of exception code. So if I go back to min-max, and remember this is dynamic so we can redefine it, and I say min-max takes some unknown number of t, of parameters, and is going to stuff them into t. And then however many of those parameters will return the min and the max of it. Now if I go back to that example where I had this call that had a bunch of parameters, it will work. Because it's going to take all of the parameters that are not already assigned to something to the left of that parameter list and stuff the rest of them into T. Was that enough example for you? Who's struggling on this concept?
The way you did it dictated that all the other arguments had to be in a T. What if you wanted there to be other arguments that weren't in a T?
Okay, so if you want other arguments that are not in a T, you need to place them before you use that asterisk one. Because otherwise, everything else will be captured by this one that says capture the rest.
So that's always in a tuple. I see. Okay.
Yeah,
okay.
and so like if you put a comma and another one after this, then it wouldn't know what to do with the last one.
Mm-hmm.
Okay? There would have to be a choice made. Now there are some languages that support this, but this is not the way this language works. So in other words, all of the other ones will go into this one that starts with an asterisk. Yes?
So the star notation has to be something that can be put into a tuple. So what if someone puts another complex data type as an argument? Is it going to return?
That's right. Tuples don't take items which themselves are mutable. Isn't that the case? A tuple can't have an element in it which is mutable because that would make the tuple mutable. So in a funny way.
So let me start on his question first, and then I'll get to yours. Actually, let me just answer yours real fast. Yes, you're right. You're right. Okay, now the more complex question. What was that? Or at least the one with the more complex answer.
Well, so there are things that people might normally put on the argument list that cannot be put into a tuple, and so would that return an error, or is the way it's said wrong that there's always something that can be put into a tuple in an argument list?
Here.
Go.
One of my elements is now an array. It could be modified at some point in time. And guess what?
I'm not. You can put an array in a tuple. This is a different problem.
Yeah, it's a problem. What happens is you're going to collapse things down to their values.
Python supports you putting an array in a tuple. It is a horrible idea and you shouldn't do it. In fact, I don't think that it's like you'll ever find anyone using that. But you can actually put a mutable object, like an array, inside of a tuple, which is supposed to be immutable, and you can even add things to it, take things away from it, and it's just bad.
Okay, so
but this is because the reference itself to the mutable object is immutable. And it's just hiding the reference from you in the syntax.
Yes.
It's okay to pass arrays as arguments normally in Python.
Right.
It's okay to pass any data type as an argument normally. But the point is that the variable argument mapping with this star here, all right, this is not specific to tuples, but for some reason he decided to talk about variable argument assignment in the middle of tuples. Because he's going to use an example that uses tuples. So this variable argument thing, it doesn't have to be, it collapses to a tuple. The tuple may have references to things that are mutable, all right? But the tuple itself won't be mutable. So when you put an array into a tuple, really, somewhere in memory, you have a reference to something else. This reference indicates that this object exists at a different location. Okay, because this is an array object. You can call functions on it and all sorts of stuff. Okay, and this is a tuple object. You call functions on it, but the functions that you call on this do not impact this thing. So when you have an embedded object in a tuple, you have a constant reference to something that might or might not be mutable. But the tuple itself is immutable. For example, I cannot swap out this array for that array. Or this list, I should say, for this list. I can't swap them out. Now I can remove 3 and 2 from this list and stick 5 in. But I can't actually get it to point to this other list. Okay?
Okay.
So that's how the tuples are immutable, but they can contain mutable elements. Alright, so let's see, where were we? Okay, so here he's showing that basically he's saying that this star inside the definition of the function gathers all of the rest of the elements. Okay? And then he's talking about the complement of gathering, which is scattering. And scattering is just basically when you walk over each element in order to do something with it. As far as I can tell, because this is not the kind of scattering that you would talk about in, say, a lot of distributed processing. Okay, this is just processing each correct element in churn. And he's saying that some of these functions that are built in actually do not function on tuples. For example, sum, even though sum, for those of you who are used to using, like, you know, the big sigma sum and doing whole lists of things, it makes sense. You could add them all together. That doesn't actually get supported because this sum is not written with the correct interface to take a list of items. It's written with an interface to take two. So now he's talking about lists and tuples. And here he's saying that sometimes you have a list of items, okay, and another list of items. And what you want to do is you want to pull the first element off of both lists, and then the second element off of both lists, and the third element off of both lists. There is a function in Python called zip. Alright? And what zip will do is it will create a construct such that it will walk both S and T at the same time and return back pairs with one element of S and one element of T. And so zip on this ABC and 0, 1, 2 will print out A0, B1, C2. In my example here, one of these is A, B, C, the other one is 0, 1, and 2. And it's returning back tuples of these. So it's a way of taking two lists and basically joining them together on a per row basis, or per index basis. Does anybody have a problem understanding that? Because otherwise some of the next examples will look really confusing. Yes?
So when you run that function, that zip function, it says zip located at, and then it gives like a location, like a memory location, instead of like the actual result. How do you print out the actual result instead of just looking at where it's at in the memory?
So you say it's doing a memory location, but if you notice in the actual output, there's no memory location that is being displayed.
Oh, I guess I'm using something else and it's actually giving me memory location. So.
May I see?
Yes.
In the grapple. In your interpreter, you get that.
Okay. So a zip is an object. Okay? Do a type on that zip. Okay? Do you see what type it is?
It's just this type. I'm using like Python instead of the regular grapple.
Is it Python 3? That's the only thing I care about. Okay. Well, anyway, the point is that this zip is an iterator. It produces elements as you ask for them. So this pair in zip, it will check to see if zip can produce another pair on demand. And if so, it will assign that actual pair of values into the variable pair as a tuple assignment into one variable name. And the print will actually print the pair out. So this means that like that zip function isn't going to like return to you the entire list of things. It is an iterator. And if you want to collect all of the elements of that zip, now in his case he's not using zip as a function, he's using it as a variable name. That's the reason he's seeing odd results, because it basically said, okay, here's your new zip at this address. Use the function list around it, and it should dump all the values that are inside that zip. Which is exactly what they do right now. They basically say list zip, and he gets an array back. The author gets an array back of all of the pairs in the zip. Now, if the sequences are not the same length, you can't get even pairs. Now, so the shorter one wins in determining the number of elements. And because the zip is returning them back as pairs, or I'm sorry, the zip is returning them back as an iterator of tuples, you can use the multiple assignment and unpack the tuples. Now, why you would want to zip both things and then unpack it straight back out, I don't know. You're probably doing something that's interesting, to say the least. But the point is that the multiple assignment still works even in for loops. And zip is guaranteed to return back 2 elements, so you could do multiple assignment inside the for loop. So he's defined a function called hasMatch. And so hasMatch will go down 2 lists, or possibly 2 tuples, and it will zip them together and then see whether or not any one line of these 2 lists match. I see a confused face, so I will demonstrate. By zipping T1, T2, we're going to get pairs, 1 element of each. For each one of those, we're going to unpack those into new variables x and y. So effectively, this will be x, and this will be y. Then we're going to check to see if they are equal. And if they are, which they are in the first element of my example, then we'll return true, saying that we found at least 1 match. but this is matching on the same index. If, for example, we had all of the same values, but they just happened to be shifted by 1, as it walked through this loop, x would never equal y until finally it exhausted all of the elements that zip can produce. And then it would return down as false. So this has match is not match by any position. It has to be a match at the same index, the way that he has written this one right here. Now, of course, we could change this various ways. We could sort it. We could do a lot of things. But the point is that the way that he has written this one, it's got to match at the exact same index. And this is what he's indicating right here, that, you know, if there is an index such that in the first tuple, the value at that index is the same as the second tuple, the value at the same matching index. So there is a function called, a built-in in Python called enumerate. And enumerate will take anything that can be turned into a sequence. Remember, strings can be turned into the sequences of characters. But it will also give an index for that sequence. So enumerate is generating this 0 and capturing the A off of the sequence of A, B, C. And then it's generating the 1 and the B. So here enumerate is generating what would have been the other element in a zip, the first element. And so enumerate basically will generate tuples that happen to also be pairs, where the first element is the index. And here he's capturing it into index and element, and then he just prints it out. So, dictionaries and tuples. One of the primary reasons why tuples get used is because we have problems with, as I had mentioned before, immutability. If you have something that you can change its value of, then because the hash code is based off of the value, all right, the hash code should change. And if we're storing it in a data structure like the hash table that's underneath the dictionary implementation, then that means that we would have to relocate it every time somebody changed one of the elements of the key. And that would probably invalidate the entire ease of use of a dictionary. So, with tuples though, you basically are guaranteeing that the elements inside the tuple, even if they are references, are constants. And you can create a hash function across those constants that's stable for that tuple. And so what you can do is you can basically capture and use those as keys. Now before, I got a little bit ahead of myself because I've read this chapter. What he's first going to do is he's going to indicate that you can collapse the items to a tuple. Okay, so you can call items on the dictionary and you get every key value pair as a tuple inside an array of every key value pair. So this is items, this is a way. You can use this in a for loop if you needed to get the key at the same time as you get the value. You can say something like for entry in dictionary.items. Okay? When you get down here though, he's saying that it works both ways. You can initialize a dictionary from an array of items, okay, where you've pre-specified the key and the value. And he's also saying that you can basically build a dictionary out of the output of zip, because zip always returns back tuples of 2 elements. And then he starts talking basically about compound keys. The way that compound keys work is that they are tuples. And so they have stable hash codes. So here he has a directory, okay? And directory is a dictionary. And so last and first is the tuple key of the dictionary. And so here we're going to assign John Cleese. It is Python after all, named after Monty Python, not the snake, a telephone number.
Oh, but is that a true statement?
Yes. Python is named after Monty Python's Flying Circus.
Oh, okay.
Hence all of the Python jokes and references. And out of curiosity, I wanted to know what this telephone number was. So I looked it up, and it is the BBC's information line. So if you're curious and you want to figure out the country code, you can call the BBC and say, I found a problem in your Learning Python book. No. Poor guys at the BBC don't deserve that. But anyway, the point is that this dictionary with the compound keys, the reason it works is because the keys are tuples, and the tuples have a stable hash code. So now that we started to talk about tuples, and tuples basically can be used in all these immutable situations, we can really let the lid off of Pandora's jar. Or open her box, or I don't know. Anyway, the point is that you can start embedding all sorts of data structures in all sorts of data structures. Because now you can basically return back a tuple of an array, a dictionary, and a string. You can return back, just about anything that you want, and just embed them into each other. And so sometimes there are conventions that make it a little bit easier. All right? When you're working with values, and you're not working with something that should be updated, just please use a tuple. Okay? If you're working with threaded code, the chance that somebody modifies something at the same time that the other thread modifies it causes tons of race conditions and problems. Use a tuple again and build the tuple you need if you need to modify it. So you remember how we modified the tuple originally by slicing off part of it and then adding the part that we had sliced off with the new value? Does anybody remember that example at the beginning? Yeah. So if you do that, then what will happen is none of the values will change in the thread that's doing the processing while it's doing the processing. Because it will either get past the new value or the old value. And basically passing a sequence to the function, tuples, they reduce some of the complexity in understanding what it is that's being passed. Okay, so he's going through debugging, and one tool that he introduces is something called struct shape. So here you can see that he is importing this struct shape function from the struct shape package. Struct shape basically walks a sequence and gives you the type of the sequence in the same kind of structure that it was walked in. So here, if you say, what is the struct shape of this array, T? And it'll say, oh, it's like a list of 3 integers. Okay? And then you say, well, what is the struct shape of this thing that is a list of lists? And it'll say, it's a list of 3 lists of 2 integers. Yes, I would have preferred if they had put a comma in the appropriate place to make it a little bit easier for humans to read. And then you say, okay, well, what's the struct shape of this thing? And it's like, oh, well, you've got a list of 3 integers, and then a float, and then 2 strings, and then 2 lists of an integer and then an integer. Yes, ouch. We will talk about classes in a couple other chapters, just like a chapter or two away. By all means, when you start getting into data structures that look like this, you need a class. Because you need to put names on what these numbers mean, so you don't forget what they mean. And so here he's zipping T and S. Remember T, the original T was 1, 2, 3. The original S was ABC. So we're going to have a list of 3 tuples of integer and string. And if we create a dictionary out of it, in struct shape, it'll say it's a dictionary of 3 items such that the keys are integers and the values are strings. And that covers tuples. And I'll skip over the puzzles for right now, even though it's got a Cartalk one in there. And then he's going to go into a case study where he talks about data structure selection. Who here has heard the word algorithm? Okay. Who here understands that algorithms are measured differently? Like some are faster than others. Okay? I see the number of hands getting progressively smaller. Who can give me an O1 algorithm for knowledge? No. It's always a joke there. So the point is that remember how we talked about how up front the dictionaries provided very fast access, provided you already knew the key. Okay, if you don't know the key, it's the same problem. You got to search through everything. All right, but if you know the key, you can go almost directly straight to the element, bypassing almost all of the other elements. Whereas a list, to see if something's in there, you have to go through each one. All right? Now granted, with a list, if you know the index, you can bypass all the elements, but the index is not a value. Whereas a dictionary, the key is a value. All right?
And then the list is mutable, right? So that the index wouldn't be reliable.
Well, the dictionary can be mutable too. You can add an extra key in there or remove a key out. And there are operations to update the keys.
But doesn't it always refer to the same thing? Whereas an index in a list would only refers to a place, not a thing.
Exactly. So like if I inserted at the beginning of a list, I would shift the indexes of everything past that beginning. Because they'd all shift down.
You'd have to do that explicitly, though.
Yeah, I would. I'd have to explicitly say I'm putting it at the beginning of the list, but it would ruin the indexes for everything in the list. If you knew that something was like at index 3, it wouldn't be at index 3 after I performed that operation. It'd be completely ruined.
Okay, that's all I'm saying.
Okay? But if a dictionary, it's either at the value of its key or it's not.
Right, no, I got it. Right.
Okay? So the point is that he's basically making an argument inside this case study that some things process much faster if you use that sort of key direct lookup than they would if you did it through some sort of Lisp-based data structure. Remember, you don't know tons and tons of different data structure types. So really all you have right now is mutable lists, immutable lists, which are called tuples, all right, and dictionaries. Now you can do a ton of programming with those data structures right there. But there are also other ones. And just generally speaking, you know, he's going to say, hey, try writing, you know, a histogram. Let's see, breaks, strips, white space, counts, birds, converts, and lower six. Okay, so he's basically saying, try running it against some small output and then go to Project Gutenberg and suck in a heck of a lot of text and watch how fast it runs. And as you convert from one data structure type to the other, you will see significant changes in speed. Okay, random numbers. I do not understand why random numbers, which is a very important thing in computers, got stuck into a case study. When you roll a dice, when you roll a die, it comes with a result, and that result is random. So far, nobody has figured out the perfect way of predicting the result of a properly thrown die. However, in computers are deterministic. And so there's not like really a random piece inside the computer. Early on, this is bizarre, but I saw it as a child. In order to generate random numbers, they would actually have dice modules attached to computers. And much like the Sorry games, where you pushed down and popped up and it threw the dice and landed inside the little plastic dome, this would happen on computers, and the die had electrical contacts on it in order to attempt to read the random number. We don't do that for very obvious reasons now. Okay? We like our computers not to have popping pieces that tend to break. So what we do is we use a very complex function. This function is really complex and is unlikely to return back a number that you will recognize what the pattern of the next number in the sequence is. Okay? It's called a pseudo-random function. Now, the reason that it's pseudo-random is because basically without direct access to the source code and knowing what the last value is, there's no way you can figure out what the next value is. All right? And they do a statistical analysis of the outputs of these values in order to try to make sure that they are distributed in ways that random numbers are typically distributed. If you do any statistics, you might know what I'm talking about. If you don't, just take my word for it. The point is that it's still a sequence. It's just a sequence with features of random numbers. And if you start at the same initial number, you will be guaranteed to move to the same next number over and over again. Okay? Now, what they're doing is they're saying that there's this function called random, all right? And it's returning a floating point. We have no idea how many values you want. So when we build a library, and when someone builds a library for random numbers, they're just going to basically give you back something between 0 and 1. If you want that to be between 0 and 8, multiply it by 8. Okay, you want it to be between 0 and 100, multiply it by 100. So we give back between 0 and 1, and we always exclude the upper limit. All right? So each time so that means that like if you really want to possibly roll a 10, you can't multiply it by just 10. You multiply it by 11 and then you truncate off the remainder.
No.
I'm sorry.
It's a modulus 10 and you add 1. Because you're moving from 0 base to 10 base.
Okay, well that's another way of doing it that was actually better. And correct. All right, but the point is that, so here you're calling random and you print it out, all right? And they have a random integer function that performs some of these math operations for you so you can't mess them up, all right? And so here's a high and low, and so it's going to pick an integer between 5 and 10. Again, you can use this random in order to pick an element out of any kind of list or tuple. And so dealing with random items is pretty useful occasionally. And of course, he introduced this random module so he could basically have you take your histogram and then write a function that will select against the probability of the elements inside the histogram. So this entire introduction to random numbers was done specifically so he could say, hey, you should write a function that would pick A 2 times as often as B. All right, for those of you who don't know how to do this, usually what you do is you start walking through the keys, and instead of mapping them by count, you map them by offset. So let's say you pulled out A first in your first value. A is 2, and then B is 3, because B is the 2 that you have plus 1. Okay? Then you call your random between 1 and 3. Okay? And you find the first element without going over. So it means that your A has a mapping of A, your B has a mapping of B. And so if it's like 1, 2, 3, if I called 2, I pulled an A. And if I called 3, I pulled a B. If I called 1, I also pulled an A. Okay, so conceptually it's not a very hard problem if you know the routine to pull things out with specific weighted probabilities. Since most of you are learning how to program, I gave the algorithm. I do think that it would be a good exercise if you try to exercise your programming ability to implement the algorithm. And then, of course, instead of doing it with letters, now you have a word histogram that you're building up, and so on and so forth. But to tell you the truth, I've been kind of jaded because the case studies that he had before were like definitely far more difficult than they needed to be because he was introducing a lot of ideas before you had any programming tools. And so these you can go through them, and if you're interested in the Slack channel, you can ask questions about them, you know, across the span of the week, and we'll help you implement them.
Can you expand on that just a little bit?
Yes, the Slack channel is a, discourse channel.
Discord. Okay, never mind. That's what.
Yes, the Discord channel. My apologies. I have been forced to use Slack recently in addition to Discord, and I confuse them both because they're almost identical when you pull them up. So here he also does a case study on histograms in such a way that you can come up with the most common word algorithm. And so what he does is he collapses all of the items into a large array of tuples, assigning the key and the value, all right? And then he builds a second array where he's appending the value to the key, and then he sorts the array. Now, when you sort by tuples, remember it's going to sort by the first thing first and the second thing second. So he's built up this histogram of words to frequency, words to count, I should say. And now he's created this array called T of counts to word, and he sorts it in reverse order. So it'll be from highest to lowest. And then he returns back the sorted version. And then in order to get just the top 10, he slices it to get just the first 10 elements. And so the most common words in Emma are apparently to, the, and, of, I, a, it, her, was, and she. If you write a book with those words as the most common words, you will share something with the author of Emma. Probably not the awards. but the frequency of the words.
It has been pointed out in the Discord that your battery is woefully low.
Oh.
Just as a heads up.
Well, that would explain.
As fun as it would be to watch it, you'll die in meditation.
Ha! The culprit is I was charging my phone. All right. Dictionary subtraction. Keys in a dictionary are treated like sets. Sets are a special mathematical idea which are not that special. You've already been introduced to them all in high school. All right? A set has an element in it at most once, or none at all. So if you add 5 to a set 3 times, the set still just has 1 5 in it. Okay? Venn diagrams are what happens when you try to visually describe how sets overlap. He's saying that he wants to create a subtract function. So here's A, here's B. All of the elements of A, he wants to remove the overlapping elements of B. Okay? Since he's not using a specialized data structure that is a set, and only a set, he's using the keys in a dictionary. Because if you set a key twice, it's just set. And so the values that he's setting in the dictionary are really irrelevant. He's just using the keys as a set. And you'll see this happen pretty frequently. When a person needs a set, they will reach for a dictionary and they will only use the keys. And usually they do something like assign the values all to 1. Okay? It's just a common programming pattern. So what he does here is he walks every key in the first dictionary, and if that key is not in the second dictionary, then he sets the value to none. And then he returns back the result, which is this dictionary that is basically the dictionary of the subtracted elements. Push the full can of soda. Random words.
Sorry, would you one more time? The values are not a set, it's the keys that are a set, or is it the other way around? You said that you can't have 2 keys, you can't have 2 values for 1 key. So does that mean...
Yes, you can't have 2 values for 1 key. So that means that if you add to a dictionary a value at a key, all right? Let's say you add the value 1 at the key. Let's say we're doing we want to know all the unique names, first names, in this room. Okay? So we'll say, oh, we'll create a dictionary for all the unique first names in this room. The key will be the first name, but we don't really have a value that it needs to be set to, so we just pick a dummy value. And we'll say, he's an Edwin. Dictionary key Edwin equals value 1. Dictionary key Evan equals value 1. Sooner or later we'll get down to a person that has a common enough name that it gets repeated. Dictionary Joe has a value of 1. Well, Joe, there might be more than 1 in the room.
That's right.
So when we hit that second Joe, we will say dictionary key Joe has a value of 1. It doesn't actually change anything. We just set the same key to the same value before. And so we have taken 2 unique entries and collapsed them to 1. And we have leveraged the dictionary to act like a mathematical set.
So another way to think about it would be to have an array, like an array, but rather than indexing by number, you're indexing it by a string.
Yeah.
Yes.
Okay, but given the group of keys here and the group of values there. Are they both sets? Is either a set? What's the... In the sections that you can't have repetitions.
They are both.
So here's how you know if it's a set. If adding the same thing twice is undetectable from adding it to it once. It's just this idea.
Okay, and so what is that true of? Is it true? Just repeat to me because reassuringly. Which
Any
one?
idea of adding the same thing twice gets you the same result of adding it once, no matter how you wrote it, no matter how you built it. It's a set idea.
So are the keys a set? Do the keys comprise a set?
The keys comprise a set because you cannot have two identical keys
That's right. And
that
do the
are
values-
somehow different.
The values don't comprise a set.
No, the values
Okay.
do not.
Okay, I got it. I got it.
Or at least they're not guaranteed to. All right. And this is a really bad way to pick a word with a frequency. Basically, he came up with items, okay, that are going to return back tuples. So it would be a word and how many times that word has been used. And he's going to pack that into word and frequency, and then he's going to take this array and he's going to add in that word frequency number of times. And the reason I say this is really bad because that means that if you use the word T 50,000 times, there is going if you use the word V 50,000 times, in this line he added 50,000 V's in an array. Just so he could use the random choice very simply to pull it out. Okay, so yes.
I don't know how important this is, but we haven't, at least to my knowledge, there's not like a set type in Python. So if you were to ask for the keys of a dictionary, it's technically a list in Python.
That's true, but it is a list that is constructed from a data structure that is guaranteed not to have duplicates.
So it's a set in the abstract sense.
It's a set in the abstract sense. That's why I kept saying anything that you use, where if you add something to it twice, you only have it in there once, is a set. There are people who will build set libraries off of things that are not dictionary keys. But in Python, it's really common to use dictionary keys as a makeshift set.
Does that make sense to you, Peter?
Yeah.
And sets are mostly useful for things on presence or absence. And then Markov Analysis is basically, we've been talking about, this is another one of those topics that goes straight over the head of most people who are learning how to program. But basically, if you have a series of things, you should be able to determine what the probability is that something would follow past that series. And so Markov Analysis, he's basically saying, suck in some data, make a map, basically make a Markov analysis chain of all of the words and what the next most likely word would be. So here, half has an A, half has a not, and somewhere down here, half has a the. So there'd be 3 elements in the Markov analysis, each weighted with a 1/3 probability to follow. This is not the kind of example I would have expected for a person who is learning how to program in Python. But for those of you who are slightly interested in data analysis, that's might be, they've got whole libraries for this Markov analysis. This is not the way that you would do it professionally either. But it might be a fun programming exercise if you really want to.
I've seen it done professionally. I've seen this sort of thing done professionally. We presented a speech that a lady was looking for. Actually, she was looking at Jane Austen books, trying to figure out if they actually were all written at the same time, like how the language had evolved between books. And she programmed something out like exactly like this. Not in Python, but yeah.
Well, I'm not saying that this is not what you would use a Markov analysis chain for. The point is that generally, if you were trying to solve a problem like this, you would go looking for one of the many available data structure modules the data analysis modules available for Python, and you would use a Markov chain engine that someone else had written. Because it is important to be able to write code for yourself, but Python already has a rich set of third-party data analysis tools, which is the reason why it is being used so heavily in data analysis. And so it might be fun for you to write a toy Markov analysis engine with Python directly, but if you were doing it, and you submitted your own, the very first thing that would happen in code review is, why did you write your own? Aren't you supposed to be using the standard one that we're using from the libraries that we're using? That said, it's a good toy program if you understand enough about the Markov analysis, because basically you're doing the same thing. You're building up a dictionary of keys to possible values that are weighted, and then you're using that random element picker based off of the weights. Given a question about, like, I have seen a this and a this. And so, what is the probability that, what's the next thing that I'm likely to see? And with that, I think we're going to close out the lecture for today. And I appreciate it greatly.